Hi everybody, welcome to lecture 12 of Electrical Engineering 331. In today's lecture, we will look at really just one problem, but it is a complicated problem. So that's why we're devoting this entire lecture to just this one problem. Now what we want to do today is to look at problem 2.5c from your textbook, but we want to solve that using the graphical convolution approach. Now, if you will look back through your notes, you will find out that we already have looked at problem 2.5c. And so let's look at what the problem states and how we solved it at that point. So in lecture 9a, we looked at this problem, and what we're told in that problem is that we're considering a system for which the step response is given by this function shown right here. Make that a little bigger for you. So this is the step function of the system. And in problem 2.5c, what we wanted to do was to find the response of that system to this input. And what we found was this. This was the output that would result from this input. And so I'm circling that answer and putting an asterisk beside it, because we will refer to that later in this lecture. Okay, and just to briefly review how we solved this problem before, what we started with was we started by observing that the input is equal to u of t minus 2u of t minus 1 plus u of t minus 2. You can see that right up there. There's u of t to make it jump up here at 0, minus 2u of t minus 1 to make it jump all the way from 1 down 2 units to negative 1, and then a plus u of t minus 2 to make it jump back up to the 0 level. So we observed that this is the expression for the input x of t. And of course, if that's the input x of t, then the response to x of t, which is y of t, will be the response to u of t minus twice the response to u of t minus 1 plus the response to u of t minus 2. So in other words, it's y step of t minus 2y step of t minus 1 plus y step of t minus 2. And fortunately, we already have y step of t given for this problem. You can see it's equal to r of t minus 2r of t minus 1 plus r of t minus 2, as we stay, and then we plug that in to here, and we did a fairly significant amount of work to end up with this answer. So that was how we did this problem before. And so now what we're asking, is there a way that we could solve this problem right here? Is there a way that we could solve this problem, find the output for this input by the convolution approach? And this is like several problems we've looked at recently. At first, it might seem impossible, because in the convolution approach, what we have is that the output y is equal to the convolution of h with x, where h is the impulse response. But we're not given the impulse response in this problem. What are we given? We are given the step response. But remember that the impulse response, h of t, is simply equal to the derivative of the step response, y step of t. So if we remember that, then we can conceivably use the convolution approach. So let's investigate that. Okay. So as I say here, let's now see if we can obtain the result using convolution. So as I just outlined, we have y of t is equal to h of t convolved with x of t, and h of t is dy step dt. This is the way we're going to find h, is by taking the information we have for y step and differentiating it with respect to t. So we have dy step dt convolved with x of t. Y step, we noted just a moment ago, y step is equal to r of t minus 2r of t minus 1 plus r of t minus 2. And then, and now, oh, and by the way, now, the fact that h of t is equal to the derivative of the step function, step response. Let me make sure I say that correctly for you. H of t, which is the response to the impulse, is the derivative of y step, which is the response to the unit step. Okay, that is very important, and you need to definitely make sure you know that for the test. Okay, now, so again, then we have expressed y step in terms of singularity functions, and now another thing that's very important is that you do know that the derivative of the ramp is the unit step. So when we differentiate these different ramp functions in here, we get unit steps with the same argument. So the derivative of r of t is u of t, the derivative of r of t minus 1 is u of, oh, and this should be t minus 1 there. This is just a little typo because it's actually plotted correctly here, but there's a little typo. That 2 should be a 1. So let me stop the video for just a moment and replace that 2 by a 1. Okay, so now we have replaced that, and that was indeed just a typo because down here, as I say, this, remember this part here represents h of t, as you can see up here, and h of t is drawn correctly with respect to this formula right here. Okay, and you notice something interesting here. In this problem, h of t and x of t are actually the same. And so we want to convolve h of t with x of t. And clearly this is going to be sort of complicated because both of these functions have multiple parts. And obviously, since h of t is equal to x of t, it doesn't matter which form we choose for the convolution integral, so I'll just choose this one. Integral negative infinity to infinity, h of t minus tau, x of tau d tau. And so I would like at this point to challenge you to stop the video and try to do this yourselves. If you can do this convolution with the graphical technique all on your own, I think you're really understanding the graphical technique, because this one is definitely complicated. So I strongly urge you to stop the video and try it yourself first. Okay, so I hope that when you tried this yourself that you arrived at the same answer that we have up here above. I hope that this was what you arrived at. But if it was not, and you'd like to see my work, or even if you did arrive at that, but would still like to see my work just to check, well then here it is. Okay, so as usual, the first thing we want to do is to concentrate on the function that has this t minus tau argument. And what we will do is first graph h of negative tau. In this case, since it is the h function we're interested in, we'll plot h of negative tau. And notice that that's just, see, here's h of t, and of course that means that h of tau, which is replace that t by tau and this t by tau. So h of tau looks like this. So h of negative tau is just that flipped or reversed, however you want to think about it. So h of negative tau would look like that. And so then h of t minus tau, remember what we will usually do is we will think of shifting it to the left, because we don't know what t is at first, but we'll think of t as being a negative number, so that means it's going to be shifted over here. And what's really important is to get these different points in the graph correct. Now notice that up here, the leading edge is at 0, and then the midpoint is at -1, and the trailing edge is at -2. And that's for h of negative tau. So when we add a t to the argument, we just add a t to each one of those points. So -2 becomes t minus 2, -1 becomes t minus 1, and 0 becomes t plus 0, or just t. So this is the graph for h of t minus tau. And once you have the graph of h of t minus tau, then you draw the graph of x of tau immediately under it, because after all, remember, this is the form that we're trying to evaluate right here, the integral of h of t minus tau times x of tau. So we want to draw this integral of, draw this function x of tau just below the graph of h of t minus tau, and now we're ready to get this problem done. Now we need to be really careful with this. Clearly, when t is less than 0, so in other words, when t is over here to the left, there's not going to be any overlap between the h graph and the x graph, because the x graph starts at tau equals 0. So we get 0 if t is less than 0. Now what we've got to do is continue to increase t and look at what happens as t is in each one of these regions. Okay, so let's first think about t being between 0 and 1. Okay, this is 0 is less than t is less than 1. Okay, if t is between 0 and 1, then that means that part of this region right here will be over here, and it will overlap with this region. So we're going to have a 1 from h, and we're going to have a 1 from this h, and a 1 from x. So this is why I have written 1 times 1 for h of t minus tau and x of tau. Now the important thing is to determine where are the limits. Now again, we're thinking of this t as being over here somewhere between 0 and 1. So the region of overlap will start at 0 and it will end at t. So that's why we have to integrate from 0 to t. And this is the end of what we get for this case when 0 is less than t is less than 1. Now the next one gets more complicated. As we get t, as t continues to move to the right, it will next move between 1 and 2. So then we say if t is between 1 and 2. And here we're going to have to be very careful, because this leading edge will be somewhere over here between 1 and 2. The midpoint here, t minus 1, then will be somewhere between 0 and 1. And so part of this trailing part here, the negative part of the negative part is going to be overlapping with the first part down here. So that's the one that there's actually going to be 3 parts. There's going to be one part where you have the negative portion, a part of the negative portion of h will overlap with this beginning positive portion of x, and then the positive portion of h will it will be overlapping here, so it will overlap some with the positive part of x and some with the negative part of x. And so we're going to have altogether 3 integrals to consider. Okay, so for the first portion where you have this negative portion of h overlapping with the positive portion of x, okay, since it's the negative portion of h, that's why the first term in the integral is -1. The second part of the integral is +1. And the region of overlap will be, now again, remember, this part, the leading edge is between 1 and 2. So the midpoint is between 0 and 1. And so we have the overlap between the negative part of h and the positive part of x will be from 0 to the midpoint, which is t minus 1. So that's why these limits are 0 and t minus 1. That takes care of the overlap between this portion of h and this portion of x. Then we'll have some overlap between this portion of x and this portion right here of h. Now both of them are equal to 1. So that's why we have 1 and times 1 here. And what should the limit be? Well, again, this t minus 1 is somewhere in here. And so the overlap of the positive portion with the positive portion will be from t minus 1 to 1. And so that's why we get the limits t minus 1 and 1 for this middle integral. And then the final thing we have to consider is, and once again, remember, t is now, in this case, is somewhere over here between 1 and 2. So we're going to have this positive portion of h overlapping with part of the negative portion of x. So we have, again, h is the first term, x is the second term, so we'll have +1 times -1. And what will be the limits on that? Well, it starts at tau equals 1, and it goes to tau equals t. So 1 to t. And again, that's the valid expression for the case when t is between 1 and 2. And now we have to look at one more pretty difficult one, and that's when t is between 2 and 3. Now let's think about that for a moment. If t is between 2 and 3, that means that this leading edge for h is now just beyond this edge for x. So the midpoint of the h graph is going to be somewhere in here between 1 and 2. And the trailing edge of the h graph is going to be somewhere between 0 and 1. So that's the first portion that we're going to have to integrate is we're going to have to integrate part of the negative portion of h with this positive portion of x. Then we're going to have the rest of the negative portion of h overlapping with this negative portion of x, and then finally we'll have part of the positive portion of h overlapping with this part of the negative portion of x. So let's put all that now in terms of a formula. Okay, again, this t minus 2 now is going to be somewhere here between 0 and 1. And so it will be, if we project, it would be down like this. So you can see we need to integrate from t minus 2 to 1, just as we have here, integral from t minus 2 to 1. And we're going to follow this model here. So the h part is negative. It's this part right here. The h part is negative. The x part is positive. So we have negative 1 times 1 d tau. Then again, t minus 1 is going to be somewhere between 1 and 2. So that means that this portion of the negative part of h will overlap with this part of the negative portion of x. So we'll have negative 1 times negative 1 in the integrand. And let's see, what will the limit be? It will be from 1 to, and again, we're going up to t minus 1. So from 1 to t minus 1, as you can see right here. And then finally, that t minus 1 is going to be somewhere like this. And so beyond that, we have part of this positive portion of h overlapping with this portion of the negative part of x. So we'll have 1 since the h is positive, negative 1 since x is negative, and then what will be the limits? It will be from t minus 1. Remember, we're looking at the case here where t minus 1 is over here. T minus 1 to 2, as you see right here. And once again, all of that is when 2 is less than t or is less than 3, which means that t minus 1 is between 1 and 2. And then the final thing we have to consider is that when t minus 2 is between 1 and 2, which is the same thing as saying that t is between 3 and 4, okay, then the only overlap we have, remember this trailing part is going to be now somewhere over here. So we'll have an overlap just of part of the negative portion of x with part of the negative portion of h. And so that's why we have negative 1 for both of them down here. And the integral will be, again, t minus 2 is somewhere like this. So the region of overlap will be from t minus 2 up to 2. So that's where we get these limits, t minus 2 and 2. And then once t is greater than 4, that means that t minus 2, this t minus 2 will be past 2. And once t minus 2 is greater than 2, or same thing as saying once t is greater than 4, then there will be no overlap at all. And so that's why we get 0 in the last case. So if you can do what we did right there and get these integrals, then you are pretty much home free, because all that remains now is to evaluate some very, very simple integrals. And if you wish, at the end, you can make sure that you have continuity at the points where the different intervals join each other, or even more easily, you can just check our answer from above. So let's see now about how to finish this problem just by evaluating these different integrals. Okay, so as we come, obviously the first one is just 0 if t is less than 0. That's easy. And when we integrate 1 d tau, we will get tau, and the limits are 0 and t. So you can see You can see that right here. And that's if 0 is less than t is less than 1. Now the next one's a little more complicated. So let's see, negative 1 times 1 is negative 1. When we integrate negative 1 d tau, we get negative tau, and the limits are 0 and t minus 1. Then we have 1 times 1, so that's the integral of 1 d tau, so we get tau, and we're integrating from t minus 1 to 1, so you see t minus 1 and 1 there. And then here we're integrating negative 1 d tau, so we get negative tau, and the limits are 1 and t. So we've put 1 and t. And that's good, that's valid if t is between 1 and 2, just as we have right here. Okay, now let's go to the next one. Negative 1 times 1 is negative 1, and the integral of negative 1 d tau is negative tau, and the limits are t minus 2 and 1, as you can see here. And then negative 1 times negative 1 is positive 1, and the integral of positive 1 d tau is positive tau, as you can see right here, and the limits are 1 and t minus 1. And then finally, 1 times negative 1 is negative 1, and the integral of negative 1 d tau is negative tau, and we're evaluating from t minus 1 to 2, as you can see there. So that takes care of 2 is less than t is less than 3. And then the rest of this is pretty easy. Negative 1 times negative 1 is positive 1, and the integral of positive 1 d tau is tau. And the limits are t minus 2 and 2, and that's for t between 3 and 4. And then finally, 0 if t is greater than 4. Okay. And now we are definitely in the home stretch of this rather lengthy problem. So 0 if t is less than 0, and then t minus 0, as we evaluate that, t minus 0 for the next region. And then for this next, now we just have to be careful, be patient with these problems. We have the negative sign, so negative is like that. And then tau evaluated from 0 to t minus 1 will be t minus 1 minus 0, the value at the upper limit minus the value at the lower limit. And then plus comes down plus 1 minus the quantity t minus 1. There's many chances here for errors, so just be patient. Again, take the value at the upper limit, which is 1, and subtract from that the value at the lower limit, which is t minus 1. And then likewise here, this minus sign, we bring down here. The value at the upper limit is t, at the lower limit it's 1. Same kind of thing for the next line. Negative sign comes down here, upper limit is 1, subtract what we have at the lower limit, which is t minus 2. And be careful to put in the parentheses so that you remember to get everything correct there. Plus, upper limit t minus 1, minus the lower limit minus 1. Minus sign comes outside, upper limit is 2, minus lower limit is t minus 1, so again we put the parentheses around t minus 1. And then finally down here, 2 is the this 2 is the upper limit minus the value at the lower limit, t minus 2. Again, we have the parentheses so we get everything straight. And now we really and truly are just about done. Okay, so the 0 comes down, t minus 0 is t. Okay, now let's do this carefully. We have a minus t, and then we have a minus 1, so that's plus 1. Then we have a minus t here, and then we have a negative of a negative 1, that's positive 1, and 1 is 2. And then a negative t, and then negative of negative 1 is positive 1. Okay, now come down to the next line. Negative of negative t is positive t. negative of negative 2 is positive 2, and 1 is 3, but we have a negative sign out here, so negative 3. Okay, here's a t, and minus 1 and minus 1 is minus 2. And here we have negative of negative t, so that's positive t right there. And here we have negative of negative 1, so that's positive 1, and 2 is 3. And we have a minus sign, so minus 3. And for the next one, we have negative t. And then we have negative of negative 2 is positive 2, and 2 is positive 4. And then the 0 comes down. And so finally, 0 comes down to 0. This is t. So here we have minus t, minus t, minus t. So we have minus 3t, and we have 1 plus 2 plus 1 is 4. So that's 4 minus 3t. The next line we have positive t, positive t, positive t. So that's where we get 3t. And then minus 3 and minus 2 is minus 5. And minus 3 is minus 8. And then minus t plus 4 there. And 0. And bring down all the conditions. And if you look up above, you will see that that is exactly the same as what we achieved before. And if you want to check for continuity, that's easy. These two regions join at t equals 0, and sure enough, at t equals 0, this is 0, and that's 0. So that checks. These two regions join at t equals 1, and at t equals 1, this is 1, and this is 4 minus 3, so that's 1. So those two check. These two regions join at t equals 2. So at 2, this is 4 minus 3 times 2, or 4 minus 6, that will be negative 2. And at 2, this one would be 3 times 2 is 6 minus 8, and this would be negative 2. So at 2, we have continuity as well. These two regions join at t equals 3, so let's see what we get there. 3 times 3 would be 9 minus 8, so this is equal to 1 at t equals 3. And at t equals 3, this is also equal to 1, because you have minus 3 plus 4 is 1. So at t equals 3, we have continuity. And then finally, these two regions join at t equals 4. And at t equals 4, this is 0. And indeed, this is 0 as well. So everything checks up. So we check for continuity, and we check for our previous answer obtained in an entirely different way. And once again, we got the same answer. So if you were not able to solve that problem before the lecture, I hope you will go back and look at it now and make sure you understand all the steps, because that was indeed quite a complicated one. And if you can get that if you can get to where you understand this well enough so that you can do that problem without referring to your notes, then I think you really do have a good grasp on the graphical convolution technique. So that concludes lecture 12, and good luck.